right, well, we'll just go through it anyways. So this talk's really going to be about two main things. So the first one is just a crash course on type classes, and the second part is, more people. Whoa. I have double the audience for the Unconference. It's super popular today. So going through type classes really quickly, and then going through what really is just the GHC user guide has an entire section on class and instance declarations that spells out what all of these extensions are and what they do to type classes. I'm going to go through kind of what each one of those is, examples of using them, and when you should avoid certain extensions. So just out of curiosity, I guess for both of you, what's your experience level with Haskell and type classes?
Quite a bit.
Quite a bit? Quite a bit? All right, cool. Well, we'll see if I have something new to tell you. So the general part of it, just starting out, is the definition of a type class from the Haskell 2010 report. So if you're familiar with this, there's Hindley-Milner type inference to have a polymorphic type system. And then to extend the type system, they added classes, which were developed kind of over a period of time between the original, what they called type classes, the newer thing called constructor classes that were merged together as an idea of the modern day type class. So really what it is the way to have overloaded functions. So you can think about type classes as just a type indexed dictionary of function definitions. So when you're going through and compiling a program, you look at the type of a function call that you had, you go look for that in all of your instance declarations, and you just kind of do that lookup and then replace your function with the instance declaration. So given a type, GHC will just look up the implementation of that function based on all of the instances that you've pulled into scope. And then type classes are a way to overload functions based on type, and then those instances behave differently depending on the context that they are used in. So instances are always imported from modules, and then depending on which instances you have imported into a new module, that behavior can change. And we'll get into that a little bit more later on in the talk. So a little bit more on a type class. So type classes were originally designed to be a really, really simple thing. So when type classes were first introduced, they were regarded as a fairly experimental language feature and therefore warranted a fairly conservative design. And all programmers want more than they're given. And many people bumped up against the limitations of that Haskell class system. So this came out of Peyton Jones, and Meyer in '97 when they were exploring the idea space for multi-parameter type classes. And why should we have it? What are all the arguments that are out there? What are the other languages that are using these type systems doing? And how do they work there? And Haskell really wanted to be very conservative. They wanted to have something that was going to be fast, that would always be decidable for all of their instance resolution. And so they just went with the simplest possible thing. And it turns out that that simplest possible thing isn't very useful. And that's kind of where GHC comes in. So if you've worked in Haskell long enough, then you know that this picture definitely resounds true. There's a core Haskell idea, and then there's GHC, which expands upon that. It implements all of Haskell in the Haskell report, but it also adds all of these different language extensions. Depending on how you count, there's about 116 of them that are unique, that add all kinds of different functionality to the language, and more of them are being added every year. So what we're going to talk about today are all of those class and instance extensions that deal with type classes in Haskell. So there's 6 class extensions and 10 instance extensions, and some of them kind of overlap with each other. But we'll go through what each one of those do in isolation and then kind of look at a few of them combined together. So what we're going to talk about is what, why, how, and when. So we're going to talk about what each extension does based on its basic definition provided in the GHC user guide. We'll talk about why it exists, what kind of cases does it, do you run into where you need these extensions. We're going to provide a couple examples of the extensions in use and compiler errors that you might get that are pretty helpful in telling you, hey, just turn on this extension and everything will work. And then on some of these, we're going to go through and talk about this use case of when. When does it make sense to use this, and when should you avoid it? We won't do that for all of them because some of the extensions are pretty simple, but on a few of the more dangerous ones, we'll talk about those examples. So the 6 class extensions, we're going to start off with multi-parameter type classes. And then just as a quick side note here, I'm going to just use bold italics to indicate all of the language that I'm just pulling directly from the GHC users guide here. There's a lot of really good information in there, and I find that most people I've talked to have never actually looked at it or didn't know it existed. But it describes all of these extensions in a lot of detail, and so I kind of pulled a lot of the descriptions as well as the code samples that I'm drawing from that user's guide. So you can always find more details there for all this stuff. All right, so starting off with just multi-parameter type classes. So what multi-parameter type classes do is exactly what the name says. In base Haskell, you can only define a class that has a single type parameter, foo a. If you wanted to have 2 parameters, you can't do that. That's illegal according to the Haskell 2010 spec. So GHG extends that. And you know what? Why would you want to do that? Well, again, type classes started off as this experimental language feature. They didn't know if it was going to work. They weren't super useful in the first iteration on them either. And then when they added constructor classes, it got a lot more powerful. And then people were able to find lots of practical use cases. And then they immediately ran into this issue of, well, why can I only have 1 parameter? So GHG extends upon this, and multi-parameter type classes kind of just allow you to be more flexible in the natural applications of type classes that exist in a lot of programs. So what does it look like? Well, here's a multi-parameter type class example class, and it's really simple. It just has 2 parameters. And when you try and compile that, you're going to get the following error in GHC, which is just too many parameters, right? So GHC is incredibly helpful here in actually telling you, in a lot of these cases, as soon as you bump into the limitations of the Haskell 2010 report, it's going to just tell you, hey, turn on this feature. And we'll see that that's pretty helpful in a lot of cases. And then there's a few where it can get you into trouble. So as an example here, if you just wanted to have your own custom version of functor that you're going to use and do some other tricks for, you need to have 2 parameters there. And it won't work otherwise without multi-parameter type classes. So this does come with a little bit of pain points for multi-parameter type classes. And that's why it was actually excluded originally. And the biggest thing is that there can be ambiguity when you're type checking. It's not as simple as the single parameter type class case. And so that's why it was excluded originally, is that it just makes the Hindley-Milner inference significantly easier, faster, and without ambiguity. So we'll talk about this more in functional dependencies, which are coming up a little bit later. All right, so the next thing is flexible contexts. And what this does is, like it says, allow the use of complex constraints in class declaration contexts. So why would you want something like that? Well, the context of a class declaration when it was first being cemented was that the context has to be simple. They wanted it, again, to just be extremely bare bones so that they could ensure that you always have a deterministic compilation, that it's never ambiguous, and everything moves on smoothly. And their definition of simple here that makes that work is that each predicate must consist of a class applied to type variables. But that can get really, really restrictive when you're actually programming something. So when you try and use flexible contexts, what you'll see is that this doesn't feel like anything, if you've worked in Haskell, as you said you had for a little while, this is not super complicated code. So you might have, for example, a simple transformer monad where you're defining lifting between 2 different, something in a monad stack. Or you might come up with something simple here where you want to be able to have basically just applied type variables in your A and list char. So flexible context changes the rules for compilation, both in the class where it's defined and in function definitions. So you might need it in another place here. So when you look at this, the compiler will also tell you that you have this non-type variable argument in the constraint. And this is a pretty safe one to get past. If you just turn on flexible context like it tells you, then you can kind of just move on pretty quickly. But this is kind of another use case. There's something really simple of just.
This means instead of a type variable, you put a type. A type, which is a listed char.
Yeah. Yep. Yeah. All right. So the next one is constraint class methods. So these allow the definition of constraints on individual class methods. So again, taken directly from the GHC user guide, this is a stupid restriction. So they got rid of it. This is actually that's turned on. Most people don't know this extension exists because if you turn on multi-parameter type class, it also turns on this extension. But if you want to see an example of what it would look like without that is, let's say I just want to have, pretend for a minute that was not a multi-parameter type class, but this is just a simple example to kind of bring it in. A class for sequences, and then I want to constrain that every element or every everything I'm going to put into my sequence has an equality instance. You can't do that without the constraint class methods in base Haskell.
So it's just a constraint on any particular method.
Yep, exactly. That's all it does. And like I said, it's implied by multi-parameter type classes, so a lot of people don't know that this one exists, but you can turn this on in isolation if you need it without turning on multiple parameter type classes. All right, so default signatures allow the definition of default method signatures in class definitions. So in base Haskell, you actually can define a default instance inside of a class declaration, but you cannot give it a particular signature. And why would that be useful? Well, generics programming is basically the reason that this exists. So when you're doing a lot of generics code, you need to be able to specialize certain default methods to have their own constraints, and then that default allows you to do some really fun things with generic programming. So here's just a quick example of what this looks like. It's taken from the generics example out of the user's guide. But you're providing a specific instance or method signature on put here that depends on these two generic representations. And those two things, if you just went with the generic default, the kind of vanilla default implementation inside of just base Haskell, you couldn't take advantage of all these generic representations that you have for that type variable A. But because you can actually now add this default signature, everything moves on pretty quickly, and you can just continue with the standard metaprogramming that you would do with generics. So nullary type classes are another thing that a lot of people don't see very often because they're also implied by multi-parameter type classes. So multi-parameter also went from not just one type, but let's go down to 0. So you have a type class that has no parameters on it. And this is something that's also, why would you ever want that? Like it doesn't seem super helpful, and it really isn't. It's used a lot of times in documentation for code. If you want to be really explicit about certain things inside of code, and I think the GHC user guide has a great example of this, of you need to assume that some mathematical principle is true. And if ever that is not true, then you have a kind of something that is explicitly defined here that says, we're going to do some work that says we have to assume that the Riemann hypothesis holds true. If that ever breaks, we know when we're looking at this function that our prime determination no longer works. You don't have anything in your constraints that's actually affecting your code, but you can use that constraint, as most people use it, to document what the features are of this function. So in a lot of cases, you might have something like you have a show constraint, which tells you what can you do with some code. Well, in this case, you have something that is going to assume that or constrain your function to use the Riemann hypothesis. And in this case, again, it's just the identity function. So it doesn't do anything except provide documentation in the method signature itself for assumptions you may have made. So the next one is functional dependencies. So a functional dependency is a way to kind of partner with the compiler to say that a specified type in your context will be uniquely specified by another type in that same context. Why would you ever want that? Well, there's a lot of cases that can kind of come up where this is really, really useful. So these are taken directly from the user's guide as well, but by including dependencies in a class declaration, we provide a mechanism for the programmer to specify each multi-parameter class more precisely. The compiler, on the other hand, is responsible for ensuring that the set of instances that are in scope at any given point in the program is consistent with any declared dependencies. So the Haskell 2010 report kind of describes this in a little bit more detail when they talk about how an expression has an ambiguous type. If in its type, and for example, for all u in the context, there's a type variable, there exists a type variable u that occurs in the context, but not in T. And they reject those types out of hand. So in this case, you're trying to have some parameter in your context that does not appear in the method, in the head of your function. For example, here u does not appear in the right-hand side of the constraints. That is kind of a hard limitation to get past when you have lots of things that have multi-parameter types, and they need to have type variables that appear inside the constraint, but maybe not actually used in the function implementation. And so functional dependencies are a way to say, we need only regard a type as ambiguous if it contains a variable on the left that is not uniquely determined either directly or indirectly by variables on the right. So directly is kind of the normal things where it's just explicitly there, and indirectly is the new capability that functional dependencies delivers. It allows you to say that given a type variable t, I know that there is only one u that will ever match with that type variable. So what does that look like in practice? Well, in this case, you might have a list of a class for collections that you want to implement, and you need to say that I need to have an empty thing. So for example, list could be an instance of this class, and I need to be able to have an empty list as just satisfying this. In normal programming without functional dependencies, you cannot actually implement that method empty for list because there's a type parameter in the class e that does not appear in the right-hand side of the method signature. There is a valid instance, that makes sense, there's the empty list, but the compiler will not allow you to do that in this case. So the way that you get around that is that you define a functional dependency that says, given a CE, I know what E is. And in this case, if for a list A, you would say, given a list A, I know that E is just A. And it allows you to kind of have that indirect inference that there's exactly one type that will unify in all these cases.
So in a way, this function dependency CE to E is a type level function. CE, it returns E.
It's not a type level function because it doesn't transform between the types. There does not have to be any kind of real transformation or morphism between those two types that has to exist. It just says that if you see int in this function, I know that the other thing is string. And it will never be anything else. There's a one-to-one unique relationship there.
I was just thinking of the way to conceptualize it.
Yeah, I mean, that is one way to think about it, as long as you're not thinking about it as type level functions in the terms of it really, it doesn't transform any values.
Right.
So there doesn't have to be any kind of value mapping. But it does say that once I see one thing, it has to mean that the other variable is this.
Right.
Yeah. All right, so that's the final class extension. But then there's still all these 10 other instance extensions. So the first one is type synonym instances. And this is one that I actually didn't realize existed at all until I went into the user's guide, because this also feels like a really stupid constraint. So why would you want to have type synonyms? Well, it's super convenient because type synonyms allow you to document your code really easily. And it just lets you define instances on those synonyms for clarity. So for example, if I want to define something where I've got some type that I want to define an instance for based on some underlying type. And it could even be, I could have just done an instance here for string. And string is a type synonym for list of char. You can't define your own instances for string without this extension because of that type synonym restriction. This was another issue that was because of the simplicity of type classes in the initial implementation, because they didn't want to have to traverse and kind of expand all these type instances or type synonyms to do the full resolution. So the second one is flexible instances, which also implies that type synonym instances, which is why I had never seen it before. I've always just gone with the flexible instances implementation. And what these do is they allow you to have arbitrary nested types in your instance head. So again, why? Well, because you need arbitrarily nested types in your instance head. So what does that look like? So this is actually the same example as flexible context. Flexible instances and flexible context go very nicely hand in hand. And in this case, this instance declaration needs flexible instances because of the list char. If you don't have it, you can't actually define something that is more complicated. So it'll tell you in GHC, just use flexible instances if you want to have a declaration for this. And I haven't seen any cases where this is blown up or hurt anyone. This is another case where it's pretty common to need this, and it's very safe to do so, and just turn it on pretty much globally if you need it. All right, so we're going to take a little detour from all these instances themselves and talk about how GHC does instance resolution. So there's a couple of things that we want to say when we're doing instance resolution, and one of them is that we don't want the compiler to just loop forever. We don't want to keep traversing all these types in a circle and have the CPU just eat up resources and do nothing. And so the rules that are imposed, what they really do is they say that you always have to make the instance matching problem one size smaller from whatever we had before. So if we were looking for 5 variable or 5 different instances before, now we're looking for 4, now we're looking for 3, and now we're looking for 2. And as long as it continues down that path, GHC, or base kind of Haskell language, is pretty happy about doing instance resolution. So there exists kind of this whole block, and we'll go through each one of these in isolation as well. But there's these 2 main rules for doing instance resolution called the coverage condition and Patterson conditions. So the Patterson conditions is broken up into 3 things, which states that for each class constraint in a given context, we say that first, no type variable has more occurrences in the constraint than in the head. So for example, this definition is illegal under that Patterson condition. because you have two type variables here, A, AA, and only one in the instance head. So you're not allowed to have those kind of definitions. The second one is that the constraint has fewer constructors and variables taken together and counting repetitions than the head. This is something that is also pretty annoying, which is this is a pretty reasonable definition for some instance. As I know that if I have a list of things that I had an instance for, then I can also show it the same way without that by just putting it into a list. And I just want to use that list representation that I defined for all my strings to make things simpler. But this also doesn't work under those constraints because it's technically one size too big compared to the instance head. The third constraint says that you cannot have any type functions, which basically means you can't use type families at all. So a type function application in principle can keep expanding forever and ever and keep getting bigger and bigger. And so rather than trying to allow the type family expansion to happen, keep getting bigger, and then check if it ever goes back down and reduces again, they just reject it out of hand from the beginning. So the second set is the coverage condition. So the coverage condition is about functional dependencies and states that for every functional dependency, where you've got kind of a set of type variables on the left of your functional dependencies and a set of type variables on your right, every type variable in this substitution mapping on the right must appear on the left. So the coverage condition itself is lifted by an extension that we're going to talk about here later. But there's another one called the liberal coverage condition, which makes finding these kind of instances that work. I'm going to show you undecidable instances in a second, but finding instances that satisfy the coverage condition, but not the liberal coverage condition, which prevents further non-deterministic loops or compiler loops from happening, is pretty hard. So in this case, the coverage condition basically states that if you have a set of type variables on the right, so in this case C, then you have to have all of these fully defined. And in this case, we didn't, because we just have a single type variable in that position for C, but nothing over here has type variables as well. They were both kind of picked, but then C wasn't. And so that is not allowed under the coverage condition. All right, so like I said, there's a way to lift these rules because they can get in your way, especially all the Patterson conditions. So undecidable instances they state on it in the GHC user's guide. If you use experimental extension, both Patterson conditions for all three of them and the coverage condition are lifted. And then the way that they ensure termination for the most part is by having a fixed depth recursion stack inside of GHC. So I believe the default limit is 200, and if you go to that, GHC will just stop, say you blew the stack. If you know that you need more than that, you can actually set with an argument what the further stack size is going to be, or you can lift that altogether. But I'd pretty much argue that you should almost never do that, but we'll get to that in a second. So why would you want to have undecidable instances? Aside from those cases before in the Patterson conditions that could be useful, one of them is class synonyms. So being able to define a whole group of classes that I don't want to write C1, C2, C3 every single time I'm going to use that combination of classes. And so you can define a class synonym in Haskell that's exactly defined like this. And then now everywhere that you had C defined or C in a constraint, it actually implies C1, C2, and C3. So that's pretty useful. The second thing is to get functional dependencies to basically work at all.
Is that necessary anymore, constraint types?
Is this?
Yeah, what I meant was, you've got like constraints and class synonyms.
Yeah.
Is that kind of unnecessary now with like constraint kinds?
I think it's simpler than constraint kinds. I think you could do the same kind of thing there, but this is just a simpler way if you don't want to go down that full path. This is just kind of an easy thing to say. In normal code, where I just had like a couple type classes, and I'm going to keep using this combination of show, EQ, and ord, and I want my app class constraints. It's just a really easy way to just kind of group those things together and then use them in all of your functions. Yeah. So functional dependencies basically require you to lift some of those conditions, and then type families basically don't work unless you have undecidable instances on in a lot of cases. All right. So what does this look like in practice? So you can define a class here, quick thing from has converter, given an A, it's going to uniquely depend, or it's going to uniquely identify the B, and then we're going to try and make an instance here that, something is showable on this B, then we want to say you can show, something else there. And this kind of stuff does not work as well, and GHC will actually tell you the 2 reasons why that doesn't work. So the first one is that variable B occurs more often in the constraint for hasConverter AB, doesn't appear on the right-hand side at all, even though it should be able to actually work backwards to get past that. And then, so for show, and then also, so B occurs both in hasConverter and in its show constraint, and it doesn't appear on the right-hand side. But this is a totally well-typed program with undecidable instances turned on, and it will work totally fine.
So I guess there's a part of GHC that just checks the rules first and says no.
Yes.
But if you put on undecidable instances, then it'll try anyway, and somehow it makes progress.
Yeah, so these rules are encoded into GHC in the compilation process. And so what undecidable instances does is it removes the Patterson conditions entirely, and it changes out the coverage condition for the liberal coverage condition, which I don't think is actually documented anywhere except inside of GHC. And then it includes that new fixed depth recursion stack size to make sure you don't loop forever. So yeah, those rules are encoded actually in the compilation process and then get removed from that process here. So when would you want to use undecidable instances? Well, the general argument is that unless you really know what you're doing, this is one of the things that GHC will tell you. If we go back to those examples here, it'll tell you just to use undecidable instances. But if you turn these on without realizing what you're doing or having everyone on your team know exactly what you're doing, it can be really easy to screw up a program that will just blow up entirely. So in some places, it'll either blow up at compile time, and it'll be really hard to figure out why in some cases. For example, why are you blowing the stack? And in some cases, you can actually still force it to loop forever in a few instances where this stack size doesn't catch you. Because there's some arcanum in there that can happen, but you can end up with programs that never compile, they refuse to.
But everything that promises all be compiled.
Yes, yep, yeah. In this case, everything is still at compile time. It's all caught there. In that you cannot get a successful compile out. But it can be really hard for especially junior team members to figure out what's going on here. So this is an instance that if you define that class for multiply, give it these instances, try to make things work, those instances in general make sense. But if you then define a function here that uses your new multiplication operator, it's going to be searching for an instance of multiply for multiply a list of B. And that instance doesn't exist, but while it just continues to churn constantly, looking for that given these instance declarations. It can't actually satisfy that instance does not exist and you're missing it, and then tell you that's the reason that it's not working. If you define that instance here, everything could be totally happy. But instead, it just says, boom, can't compile. All right. So the next one is overlapping instances. So this is, as it says, it's a deprecated extension to weaken checks intended to ensure instance resolution termination. And the reason I'm still including it, even though it's deprecated, is that the overlapping instances changed from a global at the file language pragma level to a new inline on each instance that you want to use it level. So it's still a part of that instance declaration, but you can still use it inline in 3 different flavors that we'll talk about momentarily. So why would you want to do this? Well, there's lots of cases where you want to have a special case of your instance. I want a generic when I have a list of value A. I want to have some behavior for that. But I want to specialize it that when I get a list of ints, I'm going to do something different. Or when I get a list of chars, for example, with string, I'm going to do something different there as well. So it's really convenient for those cases, and it can make it really quick to go through and add them. So how do you turn on overlapping instances? Well, it's pretty easy. Now you just go ahead. You can still turn on that extension right now at the top level, or you go in your instance declaration, and you do, for example, we'll define something as overlapping. And the choices are overlapping, overlappable, or overlaps. So overlaps is a combination of the two. Overlapping means that other instances are safe to overwrite me. So instances are, like I said, at the beginning, are defined in a module and always imported when you import a module. So what happens then is that these instance definitions are evaluated lazily. So you might not know that you have any kind of problems with overlaps until you import too many modules and they conflict. So what they wanted to do was allow a library author to define one instance and then make it, for example, overlappable, meaning that someone else can overwrite me, so that someone who's using that library and consuming it can then define their own instance that is overlapping and replace it with their own functionality. So that restriction, or that kind of design to make it more, it's actually not a restriction, that capability that they added in is one of the things that makes overlapping instances really, really dangerous. And I'm going to come back and touch on that with incoherent instances in just a second. So that's incoherent is kind of up next. So incoherent instances, same kind of thing. They are a deprecated extension. You can turn them on the top level, but now you need to turn it on inline on any definition.
You mean at the top level it's deprecated? Still okay?
Yes. Yeah. So if you turn on, if you do, in GHCI you say set -x incoherent instances, it still exists, but at some point in the future that's not determined, they're going to take it out.
But it's okay instance-wise.
Yeah. Instance by instance, you just say, and I have an example of that up next, or in the next slide. It says that you can still do it on the instance level. It's just, if I want to turn on for an entire file, you can define it at the top of your file with a language pragma until they take it out. All right, so why do you want incoherent instances? Well, what they do is they allow more than one instance to match, irrespective of whether or not there's a most specific one. And we're going to talk about what that means in just a second as well. But the reason they can be useful is that they can force instances in a particular module to work in that case, despite the fact that you might have different behaviors that could change that later on. So there's a little bit of, when they call it incoherent, what they mean is that there's two possible things that could satisfy this, and GHC is going to arbitrarily pick one. That arbitrariness can be learned, and you can figure out how to use that to your advantage. I'm not going to teach you how to do that here because, as I'll get to, I think it's a terrible idea.
How's that different than overlapping?
So overlapping will allow you to have multiple instances, but there must always be a most specific one. And I think I have an example of that coming up as well. So we'll talk about that. I kind of wanted to do those two a little bit more together because overlapping and incoherent go hand in hand. So the other thing that they can do is you can during compilation, you can force GHC to choose a particular instance, despite the fact that later on it would have picked something different, given other knowledge of future module compilation. All right, so the next thing we're talking about is this constraint searching rules, and then we're going to come back to those. And the reason I wanted to talk through this is that it kind of walks you through the process of what is GHC actually doing when it's trying to solve a constraint and pull in an instance to make that work. So the first thing it does is it's going to go look for all instances I that match the target constraint. So target constraint is a substitution of that. So that given a particular constraint, all of the instances that it could fit into as a substitution. And by substitution, that means each of the type variables that exist and in each position of the parameters for that type class. So then the first thing it's going to do after finding everything is it's going to go through and delete any candidates from that instance pool where there's two conditions that are true. And either one is that there's an instance that's more specific, and if that's true, that means that I sub y, the thing it's picking, is a direct substitution of I sub x, but not vice versa. And what it means to be more specific here is that an instance, so an instance declaration is more specific than another if and only if the head of the former is a direct substitution of the other. So that means if you had from A to int, but int doesn't go back into A. And so that's kind of what more specific means. So the second thing that needs to be true is that one of the two of them needs to be overlapping. And then they also explain here why they say either or rather than both and, because they want to be able to have this kind of functionality from a library without having to change the library. So the second thing it's going to do is it's going to say, check if there's exactly one match left. And this is kind of where the traditional Haskell rules end. If there's not exactly one match left, give up and throw a compilation error and say that this isn't going to work for what you have to find. And instead, now with these extensions, what you have is you can say, check if all of your remaining candidates have this incoherence parameter pragma turned on. And if they do, go ahead and just pick one. It doesn't matter which one. It's going to be entirely arbitrary. It can change depending on your compilation order. We're just going to pick one. If you can't, because not all of them are incoherent, then the search is going to fail. However, if it is incoherent, then the search is going to succeed and return that incoherent instance, and that's what's going to be used for that compilation. If it couldn't find anything, then it's going to basically try again later. Is essentially what's going to happen. Is that there's a possibility that when your target constraint, which may have had a lot of polymorphic type variables in it still, when later in compilation, when those are more solidified for the call sites, then it might be able to solve it later on. And so it'll do that instead. All right, so with those things in mind, how do we actually have incoherent instances? So in this case, we're going to have three instances that we defined. All of them are going to be overlappable. And if you don't also have incoherent on here, then you're not going to be able to define a method that has a type signature with f there. So the reason for that is because that instance signature is going to match to both example A and to example C here. But neither one of them is more specific. And the reason why neither one is more specific is that this list, which a lot of people don't realize, is that the list actually is a type parameter there that constrains that because of the kind of list. So this portion of it will match to list, doesn't matter what's inside of it, and then the int portion for the first one will match to that first type parameter. So in this case, you need to have incoherence to make this work. Now, like I said, you can sometimes understand what GHE is doing when it picks that arbitrary one, because it will just pick typically the first one that it finds in these lists of all these incoherent instances. So in some cases, it will make sense to have all these defined in scope in the same file and then used, and you just know that it's going to pick instance A, and that's what I'm okay with, and we're going to move on. However, there's only a few of these in the GHE user guide where they actually go out, take the time, and have a big red block that says, warning, you got to use this stuff with care. And the reason is because even if you don't have incoherent instances turned on, you can actually cause that kind of behavior of incoherence in programs where overlappable is turned on. And we'll use the example straight out of that guide as well to look at this here. So you define one module, help. It has a class myShow. You've got an instance for that where given a constraint that A has a myShow instance, we're going to have an instance for the list of those things, just do a concat map. And then we're going to find this function, showHelp, which just basically uses that instance. And that's all it does. And then in main, we're going to pull in help. And then we're going to define just our own little data type. We're going to give it a really simple instance for T, and then an instance for list of T for more specific. And then if you look at what the prints are doing here, it doesn't necessarily make sense to a lot of people. So the first thing is that you're going to use the show help from the help module, which still just uses myShow. It should go ahead and use that list for the more specific instance, but it doesn't. And then you also have another one that's the exact same call, but just using the myShow here that's in scope. And this one works fine, and we'll pull out that more specific instance. But the other one is going to rather than using this more specific instance here, it's going to match to this because of this constraint from a different module entirely. And without realizing that this instance declaration exists, you don't know what's going to happen here. And that's because when you import help, you pull in all instances. And then now you have both this instance and this one in scope. And which one is used at any given point in time really depended on the order of compilation of your program. So an arbitrary one was chosen, and because help is going to be compiled before main, this instance is chosen when compiling that function. Yes, which kind of leads me to this point. So when do you want to use overlapping and incoherent? And my answer to that is never. So if you can avoid ever using them, you should do so. And there's pretty much 4 alternatives that I've kind of laid out, which is the first one is what's used in the Haskell 98 report implementation of the class show, because you want to have a different functionality for list of char and a single or the generic list instance. So the generic list instance will go through and have list brackets and add each one piece by piece. But when you show on a list of char, you get a cohesive string out to wherever your output is. And the way they do that is they just added more class functions to show. So if you go look at what the class definition for show is, there's a show list instance that is utilized in those cases so that we can have specific functionality for a list of characters versus a list of anything else that's generic. The second thing you can do, and there's a lot of tricks that walk through this online, is use a closed type family, which kind of just allows you to have the same kind of control over which instances are chosen and which ones are going to be special and not special. That's one way to get around it. The third is auxiliary classes with kind flags. So if you would have, what you would do is define something like show prime, which has a Boolean kind flag of true or false inside of its class definition, and then switch on that for, am I going to have a special instance case and a generic instance case? And there's a lot of documentation for each one of these online if you search for any of these ideas. And then the fourth one is just, I think it is better to just start carrying around the types at the runtime and actually do type comparison and type equality analysis inside of your class definition. Have kind of a restriction that you have to have a data.data instance and then do type comparison there if you really need it. Because the runtime cost of carrying around type information is less than the developer time cost of trying to figure out what the heck is going on with overlapping and incoherent instances. All right. So the next thing, we're going to move off of this topic and move on to another instance extension. So this one is instance signatures. So what these do is they allow type signatures inside of the instance definition. And the real reason that these are useful is that you want to be explicit about certain type variables inside the documentation of inside of your function. And this is really useful in combination with scoped type variables. So in this case, we turn on scoped type variables as well. And we essentially quantify it as B so that we can use an explicit definition in kind of another auxiliary helper function down below. This is a pretty trivial case, but you can imagine more sophisticated ones where it's really useful to make sure that you have defined an explicit type for whatever your helper method is, so that whoever's looking at it, or so that GHC knows really what is the type of this function, what's it going to do. It's not generic, it is specific. And without having this instance signatures turned on, you can't actually do this, unfortunately. All right, so the next one they define is overloaded strings, which basically what everyone who's ever worked in Haskell knows about, knows why it's useful. So I can go through this pretty quickly. Basically, it's convenient. Everyone knows string sucks, use text or something more specific. How would you want to do it? Well, pretty easily. If I want to have a configuration that has a text, a byte string, and a show, or a text, byte string, and a string, and I want to just be able to write literals, string literals for each one of those, then it's really helpful to have that. So in addition to overloading strings, Haskell also allows you to overload a few other things. The first one is labels. So there's this hash foo syntax, which is called the overload label syntax, that currently exists, and it has for quite a few versions of GHC. But there's not really much utility in this function. And the GHC user guide says that they added this a long time ago because it was easy to do, and they wanted to have foresight moving towards better records in Haskell. Unfortunately, the example they use for here's what you want to use it for kind of sucks. So they kind of go through this really complicated pattern for trying to define a more extensible record in Haskell using functional dependencies and these labels, and then using the labels and the overload label syntax to dynamically define an accessor function. So in this case, you use hash x to refer to what would essentially just be these kind of instance methods for a record, which are just grab value x out and grab value y out. So it's not super useful today, but they're hoping that it will become useful in the future. Unless you're working in that domain, this extension doesn't have too much actual utility in real code.
So if you use normal record syntax, does that have something to do with that?
This is kind of, they have the hope that they will use this syntax for extensible records in the future, so that records right now are closed and they want to make them open so that you can add to it a little bit easier. Yeah, it has nothing to do with traditional record syntax today. All right, so overloaded lists are another cool extension that it's overlooked by a lot of people. And what it does is the same way that overloaded strings adds an isString type class, overloaded list adds an isList type class. And why would you want to use that? Well, because it's really useful to define things like set, maps, vectors, arrays using list syntax instead of their default things. So for example, if I want to have a map defined, and instead of just calling a from list from the map type or from the map module, I can just define it as a list the same way I would, and it kind of just saves you one extra call to from list to define that map. It's just a really convenient thing if you're doing a lot of this work directly. So the last one is undecidable superclasses. So what these are is it removes the superclass constraint that protects you from non-termination in the type checker. And the superclass constraint really is just there to protect against cyclic constraints inside of your class definitions. So because GHC would have to solve the halting problem, they can't determine if superclasses would actually terminate, so they just kick that one and ignore it. But if you know it's going to terminate, then you can get rid of that. And there's this really arcane example that they point out that actually came out of a GHC ticket for the internals of the compiler, where this was really needed, because they have these kind of recursive superclass definitions for integral domain actually is inside of its own superclass. So it is required for itself. And there's some pretty arcane stuff that's going on in there that if you can go dig into that ticket number if you're interested of why they needed it. But here's a case inside of GHC itself where they needed this functionality to continue on with the development of the tool. So that's all 16 of those. This is me, most places on the internet. And then here's a couple links to the main things I pulled from this, which are the GHC user guide itself, the Haskell 2010 report, and then there's the paper I referenced earlier on from Peyton Jones, and Meyer about the definition and exploration of multi-parameter type class space. So yeah, any questions?
Do you know if any of those extensions will make it into the next Haskell language standard, like inflexible context and flexible instances?
I was curious about that, but I didn't have the time actually to go through it and see if there's any proposals to the language standard. I would imagine that multi-parameter type classes or possibly even functional dependencies are solidified enough in GHC that it is proven, one, which is useful, which is kind of the first thing they look at is what should the language standard have? It needs to be either simpler things or it needs to be things that are really, really useful to the community. And I imagine that probably multi-parameter type classes and functional dependencies, which also implies that, so functional dependencies would be the top level thing. I imagine those will get pulled into the language core at some point. But because GHC has crushed hugs, I don't know if it really matters at this point. Like there really is, unless you're working in academics, there really isn't any other alternative compiler other than GHC anymore. So there's less of a distinction between the two unless you're in the academic spaces. Probably, but it depends on your code because Hugs doesn't have all these extensions. So like Hugs definitely fulfills the Haskell 2010 report. So if you're writing core Haskell, yeah, it's going to work totally. It'll be totally fine. I think so. Yeah, I think it's pretty flexible in that respect. Yeah, no, I mean, no one uses it anymore except for, you might have a student who had a teacher with some old material that they didn't update to say change Hugs to GHC, and then they try to install it and like things aren't working and they ask for help. That's where I've seen it recently. But yeah, I don't think, I mean, there's less of a distinction between the two for industrial programming. So I don't know what'll happen, especially because there's the whole committee for actually getting things into the Haskell report. But I'm hopeful because these are basically like core features that have been added that a lot of people will end up turning on globally in their systems anyways. Flexible instances and flexible contexts are both also very safe things to do. I think all of those can also slow down in the cases where you're not using them. If they're turned on, I think they can slow down your compilation time. But for the most part, it's pretty trivial in what it does there. So yeah, GHC can just be more aggressive when it's more constrained, especially in those rules. So like we also looked at, undecidable instances can slow things down because the rules are less tight. And so it can't reject things earlier and then move on to the next. But yeah. All right. Well, thanks for listening to me talk.